Before I get into the nitty-gritties of the physics of the Faraday cage and what it has to do with the physics of Faraday's 1843 experiment with an ice bucket, I wanted to do a simple demonstration of the power of the Faraday cage that you can do with stuff you might have around the house. So you take an AM/FM radio that is battery powered, or that can be battery powered, and you put it into a metal container. And then you turn it on and you cover it in tin foil.
Of what are the neurons that are the key hubs in the brain?
Admits it fuzzy.
Current technology.
You can hear it. Now you can't. The tin foil and the metal are blocking the radio waves. So this works even if there's holes in it, and the holes can be pretty big. Let me show you.
I'm not going to be able to do
Ready?
of animals.
Clear? Fuzzy. But how does it work? How do radio waves make it through the walls, but not through tinfoil with holes in it? And how does it block some kind of electromagnetic waves, like radio or microwave, but not visible light, which is also an electromagnetic wave? Ready to learn in detail how the Faraday cage works for lightning, for static electric charges, and for electromagnetic waves? And also learn a little bit about the history of induction, as well as Faraday's ice pail experiment and what it has to do with all of this mess? Ready? Let's go.
Electricity, electricity.
When Faraday created his cage in 1837, he also created a new concept that he called lines of inductive force to describe how it worked. Now, when most scientists hear the word induction or inductive force, we tend to think of magnetoelectric induction, which was discovered by the same Michael Faraday 6 years earlier in 1831, where he discovered that changing the magnetic field in a coil induces current in the coil. However, that wasn't what Faraday was talking about here. He wasn't talking about the kind of induction where you create a force on electrons by changing the magnetic field like he discovered in 1831. He was talking about the far older discovery that you could get charges to move by placing a charged object near a neutral object. And that discovery predated Faraday's discoveries by over 100 years. In fact, induction and conduction were both discovered in the same year, 1729, by the same guy, a 62-year-old retired clothing dyer named Stephen Gray. See, Gray was an amateur scientist with some powerful friends, like the royal astronomer John Flamsteed, but that also caused conflict with some even more powerful enemies, including Sir Isaac Newton and Newton's assistant Francis Hawksby, who got in the way of Gray's attempts to publish and to get a job in science. When Hawksby died in 1713, Newton's new assistant, John Desailliers, quietly helped Gray behind the back of his ailing boss, which is how Gray ended up with a pension at an old age home for deserving soldiers, even though he'd never been a soldier. When Newton died in 1727, Gray was free to publish without resistance. He just needed to discover something new, which he did 2 years later in the summer of 1729. That's when Gray discovered that if he rubbed a glass tube with a stopper in it, feathers would not only be attracted to the charged glass, they would also be attracted to the stopper. In other words, Gray discovered that electricity can move or conduct. As he started to study how far it could conduct, Gray found that if he tied up his line with silk, he could get the electric virtue to flow long distances. But metal wires wouldn't work, and therefore he realized that metal would let electric virtue flow away. This is how Gray discovered that every material he could find could be put into one of two categories: materials that would let the electric virtue flow away, conductors, and materials that would prevent the electric virtue from flowing away, insulators. Note that the terms insulator and conductor were created a few years after Gray by his friend John Desailliers, although it took a few more years for the names to settle down to their current definition. Then, on August 5th, 1729, Gray was conducting a typical experiment where he electrified a rod and then placed it on a line to see if feathers and fluff would be attracted to the end of the line. This time, however, Gray discovered that the feathers were attracted to line before the charged rod touched it. In other words, the electricity was induced to flow in the line without the charged object touching it. For this reason, this effect was called electric induction, although once again, the name took a little while to settle down. Gray then came up with the wild demonstration of tying up a young boy with silk and placing a charged rod near his feet and watching as pieces of fluff went to his body. This odd electric party trick kicked off decades of wild, elaborate electricity parties, which led to a plethora of new electrical discoveries. If that picture looks familiar, it's because I love it so much that I used part of it in the cover of my new book. Sorry about the shameless plug. Anyway, one of the people who got excited about doing electricity parties was a 40-year-old Benjamin Franklin. In his electricity parties, Franklin decided that electricity wasn't created or destroyed, only moved, and named the two types of electricity positive and negative. So if you have equal amount of both, then the total charge adds to zero. Franklin also flew a kite in a thunderstorm, and more importantly for the discovery of the Faraday cage, while trying to figure out how charges are distributed in a thundercloud, accidentally discovered that the interior of a charged metal jar has no charges or electric forces on the inside, a result that confused Franklin. 26 years later, in 1786, Charles Augustin Coulomb, of Coulomb's law of fame, used his very sensitive electroscope and found the same conclusion as Franklin, namely that a charged object has all its charges on the surface and the interior is protected from electric forces. 50 years later, in 1836, Michael Faraday read Coulomb's paper and was inspired to try it out himself. That is why the next year, 1837, Faraday upscaled Coulomb's experiment and built a giant cube covered in every direction with copper wire and studied the electrical effects inside the cube while experiments were conducted outside the cube. Note that at the time, one of the most precise instruments to measure electrical effects was called the Gold-Leaf Electrometer, which is a simple device made of two thin pieces of gold in a glass case to block the air currents. And those pieces of gold are connected with metal to a plate on the top. The idea is if you place the charged object on or near the plate, the gold would become charged either with induction or conduction with the same charge and then repel each other. The more charge, the more they repel. This is why when Faraday was in the Faraday cage, he said, "I put a delicate gold leaf electrometer within the cube and then charged the whole by an outside communication very strongly and for some time together. But neither during the charge nor after the discharge did the electrometer or air within show the least sign of electricity." Faraday had a theory of why the Faraday cage worked. And his theory was that all charged objects emanate lines of inductive force, or we would now call them electric field lines, and that conductors let electricity flow easily to cancel out these lines, and insulators do not. We basically think this today. However, at the time, scientists were decidedly uninterested in Faraday's thought process here, and he got into multiple debates with people who politely tried to get Faraday to see the error of his ways, especially an American scientist named Dr. Hare. Faraday had trouble standing up for his point of view, as one, he really hated controversy, and two, his health had started to falter by the late 1830s, and doctors didn't know what was wrong with him. It seems likely that he was suffering from confusion and memory loss due to handling heavy metals in the 1820s without protective equipment. In fact, his health kept him completely away from science between early 1841 and 1843. It was only in late January 1843 that he could even start to read literature again, even a little bit. It was around this time, actually February of 1843, that Faraday came up with his famous ice bucket experiment that he said are the expression and proof of certain parts of my view of induction. Faraday knew from Benjamin Franklin's old 1755 experiment that if you charged up a conductive cup, then the inside would be shielded from electric forces. And even if you had a ball touch the inner surface of the container, the ball would still not gain a charge. To Faraday's mind, this all made sense thinking about his lines of inductive force or electric field lines, but didn't really make sense to anyone else. That's why he took Franklin's 1755 experiment and turned it on its head. He took a metal container, which in this case was an ice bucket, thus the name of the experiment, put it on an insulating stand, but charged the ball instead of the bucket. He then connected the outside of the bucket to a Gold-Leaf Electrometer. With the electrometer, Faraday could tell that when the charged ball went into the bucket, the outside of the bucket became electrified like the ball was. If the ball was removed, the bucket lost all electrification. This proved to Faraday, and basically to everyone else, that this was a question of induction, as the ice bucket got a charge without the ball touching the ice bucket. What is going on? Well, Faraday imagined that the charged ball was emanating these inductive lines of force, or electric field lines, which moved the charges in the conductive ice bucket so that the outside of the bucket had the same charge as the ball, and therefore the inside of the bucket had the opposite charges of the ball. So the ice pail is still neutral, but it is not evenly distributed. If the ball is removed, the lines of force are also removed, and the outside and the inside of the bucket are once again neutral. Note that Faraday's theory worked if the positive charges are moving, if the negative charges are moving, or if both the positive and negative charges are moving. Because at the time, they had no idea if positive charges were moving, negative charges were moving, or both were moving, because this experiment predates the discovery of the electron by 54 years. That's not all. Faraday also found that if the charged ball touched the inside of the bucket, the outside charge stayed the same, but the ball and the inner surface lost all of its charge, thereby proving that the inside charge in the bucket was equal and opposite to the charge on the ball. Faraday found that was true for positively or negatively charged balls. If they touched the inside of the conductive pail, the ball lost all charge and the ice bucket ended up with a net charge on the surface. Either way, you are back to Franklin's 1755 experiment or Coulomb's 1786 experiment, where a charge is on the outside of a charged conductor and a neutral ball is shielded from all electrical effects on the inside, and the electric field on the inside of a conductor is zero. This is how a Faraday cage protects you from lightning strikes, either natural from a cloud or artificial from like a Tesla coil. See, when there is a lightning strike, a burst of electrons hits the surface. The electricity then flows on the outside of the cage, and then either into the ground or stays safely on the outside of the cage if the cage is insulated, leaving the inside of the cage completely undisturbed. This is true even if you are touching the inside of the cage, as long as your fingers don't poke through the holes. In fact, one of the major reasons for the small holes in the cages used in Tesla coil demonstrations is to keep your fingers from poking through the holes, not to keep the lightning from going into you. This is why you are safe in a metal airplane or metal car if it is struck by lightning, even though they have large insulating windows. Okay, but how does the Faraday cage protect you when the charge is on the outside of the cage? How does it protect you from the electric field? So imagine a Faraday cage is near a static electricity generator. For example, a Van de Graaff generator has a motor that spins a rubber belt against a metal comb. The metal comb collects extra electrons and leaves the metal sphere on top with a positive charge and between 50 and 150 kilovolts. Now, many of you have seen the demonstration where you stand on an insulating stand, touch the generator while it's charging up so that you lose electrons, your hair gets all positively charged, and they stand up and repel each other. But what you might not know is if you stand near a Van de Graaff generator, your hair will also stand up a little bit, just not as much. And that is because the electrons in your hair will move towards the generator. So your hair near the generator will become negatively charged. Your hair far away from the generator will become positively charged. And both ends will end up sticking up. Now imagine you're in a Faraday cage. In this case, some electrons in the cage near the generator will move towards the positive generator and leave the other side positively charged. In this case, the Faraday cage is neutral, but it has a net positive charge on one side and a net negative on the other. Inside the cage, you are once again shielded from these electric forces. And so within the cage, you will find no electric effects. But if you pop your head out of the cage, then suddenly you will find your hair or any tinsel will stand up because you are no longer protected by the movement of the electrons in the cage. That still doesn't explain how the Faraday cage protects you from electromagnetic waves like radio waves. That started with Faraday too. See, back in 1832, Faraday had the idea that magnetic forces and electric forces take time to travel in space and can make waves in the air, like the vibrations upon the surface of water or those of air in the phenomena of sound, and most probably to light. By 1846, Faraday had the even more radical idea that not only could electric forces and magnetic forces make waves in air, maybe light itself is composed of vibrations of these forces. This idea was even more hated than Faraday's idea about lines of forces, and it was almost universally ignored at the time. Fast forward 18 years to 1864, when a 33-year-old mathematical physicist named James Clerk Maxwell wrote his masterpiece, A Dynamical Theory of the Electromagnetic Field. In this paper, Maxwell took Faraday's ideas of electric lines of force and magnetic lines of force and combined them with the previous equations and ideas about electric forces and magnetic forces. In addition, Maxwell created equations for describing vibrating electric fields and magnetic fields that moved at the speed of light, inspired by Faraday's paper of 1846, writing that the electromagnetic theory of light as proposed by Faraday is the same in substance as that which I have begun to develop in this paper. Not surprisingly, Maxwell's ideas were almost as controversial as Faraday's ideas were 9 years earlier. However, as time passed, there became a small group of tinkerers and engineers and physicists who called themselves Maxwellians and tried their best to tackle the complex mathematics of Maxwell's paper, including an English engineer named Oliver Heaviside, who in January 1885 published his mathematical interpretations of Maxwell's equations, which led directly to the modern form of Maxwell's equations. The following year, another Maxwellian, a young German scientist named Heinrich Hertz, was showing his fiancée around his laboratory when he told her that one of his devices, called an induction coil, would make bursts of vibrating electric current around 50 billion times a second. Hertz's fiancée, Elizabeth, wondered if it would make light, as he had told her that a vibrating current would make an electromagnetic wave. Hertz told her that it was far slower than light, that tends to vibrate in the hundreds of trillions of times per second. But it started him thinking, maybe it would make a light, but only make an invisible light. light. That was why in 1887, Hertz added an antenna to the induction coil and discovered that they could be caught in a receiver, and this invisible wave did move at the speed of light. Hertz had discovered radio waves, which is why frequency is now measured in hertz in his honor. That's not all. In July of 1889, Hertz actually tested out his new wave on a Faraday cage and found that not the slightest electrical disturbance would be detected in the wire in whatever direction the waves were sent through the apparatus. Okay, but how does this work? In a radio, an electric signal vibrating between 30 and 300 billion times a second is placed on an antenna, which then causes electrons in the receiving antenna to vibrate at that same frequency. Now, the reason this is called an electromagnetic wave and not just an electric wave is because, according to Maxwell and Heaviside, when you have a vibrating electric field, it also induces a vibrating magnetic field. Those fields move perpendicularly to each other at the speed of light. Now, when the electric field from a radio waves hits the electrons in the Faraday cage, it causes them to vibrate in sympathy and cancels out the electric field inside the cage. Note that just as in the example of the single static charge outside the cage, the electrons in the cage move as to negate the electric field in the cage, but it still exists outside the cage. Now, we can't see it, but just like visible light isn't in a single column, radio waves tend to be dispersed throughout the room, and therefore you need the Faraday cage to be completely surrounding the object in order to block out all of the radio wave. However, the Faraday cage does not need to be solid. It can have holes in it, as long as the holes are smaller than the wavelength of the light. A rule of thumb tends to be you want the holes to be about smaller than 1/10 of the wavelength of the light. Now, with radio waves, this is really easy. AM, FM radio tends to have a wavelength of between 1 meter and thousands of meters. For example, the late great radio station 104.5 KFOG has a frequency of 104.5 million hertz, and therefore a wavelength of 2.8 meters, which means that a cage with 28 centimeter or 11-inch holes should kill the signal. This is even easier to block out the radio waves that come from Tesla coils, and yes, they do produce radio waves, because they tend to operate on very low frequencies. For example, according to the creator of the Mega Zapper, the Tesla coil that I was zapped with when I stood in a Faraday cage, it ran at 112 kilohertz, which has an astonishing wavelength of 2,678 meters, or 1.66 miles. However, as I said, the big danger with the Tesla coils is not from the radio waves that come through, it's from getting struck by lightning. And the reason that you want those cages to have small holes is to keep curious people from sticking their finger through and then getting struck by lightning because you're on the outside of the cage. Now, as the frequency increases, the wavelength decreases. For example, microwaves that heat your food tend to be run at 2.45 gigahertz, and therefore they have a wavelength of about 12 centimeters, which is why the grating on your microwave oven can have little holes in them and still protect you from getting cooked by their E&M waves. By the time you get to infrared, the holes would have to be so small that you can't see through them anyway, so most people make infrared protective devices without any holes in them whatsoever. Note the Faraday cages protect you because of the movement of the electrons in the cage. It is an electric effect. Because of this, Faraday cages can protect against static electric fields and varying electric fields, as all electric fields create a force on electrons. They can also protect against varying magnetic fields, as a changing magnetic field could move an electron and make a current, just as Faraday discovered in 1831. However, Faraday cages cannot shield against static magnetic fields, which is why a compass works fine inside an airplane. So that's the physics of the Faraday cage. I've made a ton of other videos if you want more details, including one on the history and influence of the Faraday cage, ones on the history of the different fields, as well as ones on Faraday, Maxwell, and Hertz. I particularly think my video on Maxwell needs a little bit more love. However, I realized I haven't yet done a video on Oliver Heaviside and how he made a modern version of Maxwell's equations, and what each individual equation means and how they were inspired by the scientists before them. The first of these videos, how Maxwell Heaviside's first equation was inspired by Coulomb and Faraday, is next time on the Lightning Tamers. If you like learning about the real history with the real science, you will love my new book, The Lightning Tamers, available on ebook form, paperback and hardback on Amazon and through your local bookstore. Check out my website, www.kathylovesphysics.com. You will find information about the book. You will find scripts for my videos with citations. You will find a way to download the first 3 chapters as an ebook if you want to. You will find a way to join my Patreon page if you want to. Thank you, patrons. And by the way, anyone who joins my Patreon at $8 a month or more gets a free ebook today. You don't even have to wait till it's out. The book is out October 12th. Thanks so much. You stay safe and curious. Bye. Note that the terms insulator and conductor were actually created by Gray's friend, John Desailly. I can't say his name. I'm really trying. I listened to it and I'm still having trouble. And you put it in a metal container. I'm putting it into this. Okay. And then that's what happens with real experiments. That's what I get for self-promoting. Okay. Stay. Good. Here, wait. So make sure to pre-order it. Make sure to go to Goodreads if you have a Goodreads account and say how great it is. I don't know.